Welcome to this explainer on material geometries. We're going to dive right in today. We interact with solid materials every single day, right? And sure, we all know there's some complex chemistry at play, but today we're going to trace exactly how the invisible, surprisingly simple, crystal architectures holding them all together actually form. To really get a grip on this invisible world, we need to start with something you've probably got sitting in your pantry right now. You know that old jar of honey? The one that's been sitting around for months and suddenly grew those rigid, crunchy sugar crystals? Well, that little annoyance for your morning tea is actually a perfect macro-level example of the exact science we're analyzing today.
Section 1. From honey to atoms. Let's look at nucleation basics.
So let's scale down from that sticky honey to the literal atomic building blocks of solid metals. We do this by looking at the nucleation process. That everyday honey phenomenon perfectly illustrates this sequence. First, liquid molecules slow down. Second, they deposit onto some kind of rough surface. This could be a tiny scratch on the inside of the jar, or, maybe a piece of string if you're making rock candy. Third, these rough spots serve as low-energy nucleation sites for the sugar. And finally, step 4, once they find that comfortable low-energy spot, they begin forming regular, repeating patterns, literally building on top of each other piece by piece.
And here is the absolutely crucial point for us. The exact same process happens when molten metal cools down. Just imagine heating a piece of metal to thousands of degrees until it's completely liquid, and then letting it cool. Seeking a lower, much more comfortable energy state, the atoms essentially lock together to form metallic bonds. Just like those sugar molecules finding a scratch on a jar, metal atoms organize themselves into their very own microscopic repeating blueprints. Now, in materials science, we call these repeating arrangements crystals or grains. Honestly, the two terms are pretty much synonymous here. And this brilliantly highlights the great divide in solid materials. On one side, you have these highly ordered crystals or grains. We're talking total macroscopic organization. On the flip side, you have amorphous materials, like glass. Amorphous materials completely lack this underlying repeating structural order. Their atoms are just sort of jumbled together without any blueprint at all, living in complete structural chaos. But today, we're focusing squarely on the organized ones.
Section 2. The two-dimensional analogy. Simplifying structures.
Trying to describe the exact position of a million individual atoms in a crystal is, well, entirely impractical. We would literally be here for weeks. So, to break this massive network down into something digestible, think of a two-dimensional analogy, like a tiled brick classroom wall. Instead of mapping out every single brick on that massive wall to explain the design, you can completely describe the entire pattern by simply defining the height and width of just one single brick, and then accounting for half of the grout line between them. If you know the dimensions of that one repeating building block, you magically have the blueprint for the entire wall. But as we look at these repeating brick building blocks, it introduces a pretty fascinating geometric test. What shapes can actually be used to cover an area completely, without leaving any empty spaces or voids? Well, this test reveals the rule of translational symmetry. You can take shapes like squares or parallelepipeds, where opposite sides are parallel, and slide them right next to each other to perfectly fill 100% of an area. They have translational symmetry. But try doing this with circles or unrotated triangles, and they fundamentally fail the test. No matter how tightly you squeeze those circles together, you are always going to leave empty voids. They completely lack translational symmetry.
Section 3. Filling three-dimensional space. Cubic symmetry.
So now that we've solved the 2D puzzle on our flat wall, let's step out into the three-dimensional world where physical materials actually exist. The most natural 3D extension of our flat, space-filling square is, of course, the cube. A cube can be perfectly translated up, down, left, right, front, and back to completely fill a solid volume without leaving a single microscopic gap.
And this brings us to a really convenient, almost magical result of nature. A vast number of physical materials inherently possess this exact cubic symmetry. This is absolutely fantastic for us, because we humans already naturally love our 90-degree orthogonal X, Y, and Z axes. It makes mapping out these structures incredibly intuitive when nature kindly decides to build in perfect little cubes. Section 4. Unit cells and lattices. Defining architecture. Having proven how these geometric shapes efficiently lock together, we can finally apply the specific terminology that material scientists actually use. First up, the unit cell.
Instead of just calling that single repeating chunk a building block, like we did with our 2D brick wall, scientists refer to this foundational 3D shape as a unit cell. It is the core repeating unit of a much larger structure.
To define the exact size and dimensions of these unit cells, we describe their lattice parameters. Now, in the case of a perfect 90-degree cube, it's wonderfully simple. Because all sides are equal, we just need a single edge length measurement, which is commonly represented by the lowercase letter a. If it were a stretched out shape, like a rectangle pulled into 3D, we need an a and a b parameter. But for our perfect cube, just a covers it perfectly. And that brings us to the lattice. When you repeatedly stack these unit shells together, front to back, up and down, left and right, across three-dimensional space, they generate a lattice. Think of it as a repeating geometric framework. It's actually very similar to a garden lattice or a trellis you might use to grow climbing vines. Only in this microscopic framework, individual atoms are precisely assigned to specific intersecting points across that vast 3D grid. So the crucial takeaway here is that the solid objects we interact with every single day aren't just random clumps of matter. They are highly organized architectural masterpieces at the atomic level. As we wrap up this explainer, I want you to ask yourself, if simple cubes form the unseen foundation of so many common materials, what other hidden geometries are secretly shaping the physical world around you? Keep that in mind the next time you pick up a piece of metal or, look at that old jar of honey. Thanks for exploring with me.